So we're talking about nucleophilic substitution. Forget about the word nucleophilic or anything like that. A substitution, just a substitution, and neither of these, just a general idea of a substitution, would be that you would have some sort of a carbon, because I mean this is organic chemistry, right? So you have some sort of a carbon connected to various groups, and it would have something that's called a leaving group. We'll figure out what a leaving group is later. These do not have to be the same. They could be whatever. It could be a benzene ring or a hydrogen. Who knows what it is? I'm just, for now, writing R and showing that they don't have to be the same. So I'm going to call it R with a stick, and R with two sticks, just to say that, who knows? They could all be hydrogens. They could all be methyls. I don't know what they are. But you have that, and you have a nucleophile. And this is your before picture. And somehow something replaces, so this is your after picture. And let's say the nucleophile is negatively charged, because there's cases where it's neutral, there's cases where it's negatively charged, so let's just take one easy example. It's negatively charged, fine. That's what you have before. That means you took this and you took that and you put it in a flask. You came back tomorrow, and you don't have these things in the flask anymore, you have something else. No longer is the thing called a leaving group attached to the carbon. Now it is a nucleophile attached to the carbon. And the nucleophile is not on its own with a negative charge. The leaving group is now on its own with a negative charge. So this is what chemists found however many years ago. And they try to figure out how it could be done. And when describing a mechanism, you guess the mechanism. I know that's like at first for a student, oh my God, how can you guess something? No, it's really simple. In chemical reactions, bonds break and bonds form, and this is a simple one because there's not a lot of bonds breaking and not a lot of bonds forming. There is only really this bond that is breaking. This bond doesn't break. It's there in the beginning and there at the end. This bond doesn't break. It's there in the beginning. This bond doesn't break. It's there in the beginning and the end. So the only bond that breaks, you're breaking a carbon to leaving group bond, and then in your products, you make a carbon to nucleophile bond, right? Like we should say this to like be as complete with what's going on here in general. So how could you imagine, knowing nothing about chemistry at all, that these can happen in time? I'm not saying you know anything about what a bond is. A student that's completely ignorant on chemistry, they'll be like, what's a bond? Oh, they're connected. Oh, okay, so you're saying to me that these two things are connected, and then I come back and now later on these two things are connected. Like first it's this and then it's this. Okay, so come up with some ideas of how that could happen in time. And one of three things becomes the possible answer. Either first a bond is broken, these things hang out, float around, and then along comes the nucleophile and attaches, right? We're trying to say in time. In time, you need to break a bond, you need to make a bond. So like what are the ways you could do it? You could break a bond first, wait some period of time, then make a bond. You can make the bond first, wait some period of time, then break the bond. Or you could do things simultaneously. Like if there's two events, you could do first event, second event, first event, or both. So here's one option. Break, then make. Here's a second option. Make, then break. There's a third option. Both at the same time. And it turns out, when you ask a chemist, are all of these things possible? For carbon, all three of these things are not possible. One of them is illegal for carbon. If you break a bond, let's say you break that bond, carbon loses its octet role. But is that illegal? If you do it simultaneously, then you're doing a switch. Is that illegal? And then there's an option for number two, make a bond. So that means the nucleophile will make a bond. It's going to hang out like this for some period of time, and then you're going to break the bond to the leaving group. I hope everyone sees right away that 5 bonds on carbon is completely impossible. So you cannot make the bond first. You could only break it. So either Either you make the bond after you break it, or you make the bond simultaneously with breaking it. And chemists knew early on that these are your only two options. So they did a whole bunch of experiments and found those two options. Sn1 and Sn2 turn out to be those two options. In one of these cases, both the bonds break and form at the same time. And in the other case right there, it's in two steps. The bond breaks first, and then some point later, a new bond is formed, right? And it first is a little counterintuitive, because we need to know what Sn1 and Sn2 stands for. See, look, when you do it simultaneous, it's all in one step. And when you break the bond first, then make the bond, it's in more than one step, right? So what is Sn1, Sn2? When a student first starts learning this, they think, oh, Sn1 must be one step, Sn2 must be two steps. It's not. The name Sn1 is substitution nucleophilic unimolecular. And that's what the one stands for, unimolecular. It stands for the rate law. And the rate law is what we learned from Chem 2, is the rate of the slow step, right? The rate limiting step. And there's one molecule in the rate law in that rate step. I will remind you how to write rate laws. She had to have said it like I'm saying it. Sn2 stands for substitution nucleophilic bimolecular. So you have two molecules participating in the rate law. It's a bimolecular reaction. So it turns out that Sn1 is done in more than one step, while Sn2 is done in only one step, and that's where you've got some confusion. It's going to be even more confusing when you have neutral nucleophiles, and it turns out that Sn1 is done in... So the easy way to say it is for a lot of these reactions, Sn1 is two steps and Sn2 is one step, but then you'll see later that this is at least two steps, and that's at least one step. So some Sn2s are in two steps, and some Sn1s are in 3, 4, 5, or 6 steps. So I'll show you the general stuff, and then carbocation rearrangements, I'll try to show you what that is, but we need to know the mechanism first before we go into what's carbocation rearrangements. Trying to learn all that at once is going to be nearly impossible, I think. It might confuse you more than it helps you. But what is going to be true no matter what, whether it's Sn1 or Sn2, you have to have a carbon that is sp3 that has a leaving group attached. Like, you're not going to be able to do Sn1 or Sn2 on this kind of a carbon, on any of the carbons in this compound, because none of these carbons are sp3. Do you see that's sp2, 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 sp2? So you need sp3 minimum. So over here we're going to start with, let's say, a carbon that has an R, an R, an R, and a leaving group. And to show these R's are different, again, I'm going to write R, R prime, R double prime. And you have this first step that I'm going to draw as an equilibrium, and the first step is the leaving group just leaves. It isn't like what I showed you before, where the nucleophile comes in and attacks from the back and pushes off the leaving group. This one, the leaving group just falls off. And we would say, wow, that's crazy. So I have a molecule in my hand and the leaving group just falls off. No, there's conditions that you put it in where the leaving group falls off, and that always has to do with solvent, and we'll deal with that. But the general steps are that the leaving group leaves, and the way that it leaves is it takes electrons with it. So imagine the leaving group had a positive charge. If it took electrons with it, it became neutral. If the leaving group was neutral and took electrons with it, it would become negatively charged. Do you see if it... And then, of course, if that broke off and became negatively charged, absolutely you have a carbocation that forms. which, by the way, is an acid because if there's anything electron poor, it's something that doesn't have an octet rule and is positive charge, right? So what could happen right now? Do you see how it could reverse? Can you imagine if you have a carbocation that doesn't have an octet rule and you have something that's got a negative charge in a lone pair that could just attach and go right back to where it came from? That's possible. This you call step 1. And then there's step 2. And in step 2, the carbocation maybe could react with something else in the flask. It doesn't necessarily have to react with the nuke. It could it doesn't have to react necessarily with the leaving group. It could react with a nucleophile if there happens to be another thing that has electrons in the flask, right? Like I put, as an example of this, in my flask I put this substance, and soon we will come to know bromine as a possible leaving group, right? So I put that into a flask with water. What could happen is that this bond could land on bromine and make Br minus and a carbocation over here. And now either Br could attach or water could come in and attach. So anything that has lone pairs can come in and attach. So this thing could react with the leaving group and go back, or it could react with a nuke. And the nuke can attach. A nucleophile is anything that's a base. What is a base? Something electron rich. So there's actually two things that really qualify for a base. And we should have done that. We should have said that, but we're missing an entire chapter in discussing Sn2 and Sn1. We're missing acid-base. And so to say it in the fastest way possible, if you think about what things can be a base, it's anything that has electrons. So if I look at this compound right here, if I look at this compound, let's say right here, what parts of this molecule can be a base? There's, like, the sigma bonds have electrons, but that's not, I wouldn't call that really an electron-rich region. I wouldn't say that a sigma bond has extra electrons by any means. They're used in bonding. But a pi region, a region that has an extra stick over here, that's a little bit of a base. That's electron-rich. And this is multiple pi bonds. That's even more electron-rich, maybe. This has lone pairs. It's electron-rich, but it's neutral, so it's fine. This has lone pairs and it's negative. That's much more electron-rich than this. This has lone pairs and it's negative, but it's resonance stabilized, so I would say it's not as electron-rich as something that's not resonance stabilized. Do you see that? So when we're talking about what's a base, you end up having that a base can be a lone pair, a pi bond, and in very rare cases, a sigma bond. That's really the discussion that we just saw. And if we use a lone pair as a base, and not in an acid-base capacity, but like in the rest of the book, if we use a lone pair as a base, you're talking about things like Sn1, Sn2, blah, 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 E1, E2, all of those kind of things. And if we use a pi bond as a base, then what we're looking at here is alkene chemistry. You know, like a pi bond, like an alkene reacting with HBr, for example. Have you seen this before? And the double bond grabs the H. Like, wouldn't a base react with HBr and take an H and push off? We'll deal with that in a moment after I explain something about stability. And then you'll realize exactly what to do, I hope. So the nucleophile would attach to here. I'm not showing it attached to a positive charge. I'm showing it attached to the carbon. It's just the positive charge is in the way. You really should show the lone pair attached to there. Please don't make rookie mistakes on the exam, like push a positive charge. We push electrons, sticks, and dots. And we show the arrow going to where they're going to end up. Here the electrons are going onto the leaving group. That's why I show a lone pair on the leaving group. If I wanted the leaving group to reattach to the carbon, I would show an arrow going to reattach to the carbon, or show an arrow reattaching to the carbon. And this over here ends up being the substitution. With nuke. That's it. And the reason it's called an Sn1 substitution is because which of these is the rate determining step? The rate determining step is the slow step. But how the hell would you know what the slow step is? Let's analyze what we've learned in orgo so far. Do you think it's easier to break the octet rule for carbon, or do you think it's easier to make the octet rule complete for carbon? It's probably easier to complete the octet rule than to ruin the octet rule, and that's why I have an equilibrium in this step. I'm going to always draw equilibrium arrows for steps that are uphill, and I'm going to draw a straight arrow for steps that are downhill in terms of energy. So this is uphill in energy, that's downhill in energy. So this is going to be our slow step. And if you remember Gen Chem, if you have, let's say, A plus B goes to C, and then another step, C plus D goes to E plus F, like whichever one of these is the slow step, you would write a rate law for it. Imagine this is K1, and this is K2, and this is a whole mechanism. Let's say this is the slow step, right? You would write rate is equal to K2 times the concentration of C times the concentration of D. If you didn't know that it was an elementary step, one step of an entire mechanism, then you would write to the M and to the N, and then you would use those experiments like 1 and 3 and 2 and 4 to figure out, you remember you hold one thing constant and vary the other. But because this is one step of a known mechanism, then you know it's to the first power and to the second power. Since you see two molecules in this rate law, it's bimolecular. If you would only see one molecule in the rate law, let's say it was that, then it would be unimolecular, right? So if I'm going to write the rate law for this slow step, then the rate law is going to be rate is equal to K times the concentration of the reactant. But in this case, this is the slow step. It's difficult to break this thing apart. And once it does, boom, it goes, right? So it's just this molecule in the rate law, because there's only one reactant in the slow step, right? There's not two reactants. If this was a slow step, you'd say it's a bimolecular process. But if this is the slow step, then it's a one molecule unimolecular process. So over here I write carbon with an R, leaving group, prime, double prime, so on. Do you see why it's a unimolecular rate law?
Yes, so next time we have to always like leaving group.
So here's the idea, and organic chemistry is like refining Gen Chem. In Gen Chem, you learned that a reaction is faster when you have a bigger K, and it's slower when you have a smaller K. Now we're starting to learn what affects the K, like what makes a K bigger and what makes a K smaller. If you see the concentration of this substance in the rate law, then that substance is important for the rate law. You do not see the concentration of the nucleophile in the rate law. That means it doesn't matter who the nucleophile is. I can use a shitty nucleophile or a better nucleophile. It's not going to help the reaction go faster or slower because the rate determining step is only on this molecule. But because you see this in the rate law, then all of its parts matter for what K is. For example, the better the leaving group, the better the K. The better the R groups, the better the K. So they are all going to affect how important the K constant is. And we can write factors that K depends on. K depends on three things, it turns out. And you'll see why it's three things here. One is the identity of the leaving group. So if you have a really crappy leaving group, the leaving group's not going to leave, and that's it. K, the reaction's going to have a really small K, and there won't be any rate, and there won't be any reaction. So we need to figure out who the good leaving groups are. And we'll talk about that in a second. The next thing that it depends on is the type of carbon, because it'll matter if these are hydrogens or carbons or anything like that. So the identity of the carbon. And I could go ahead right now and just tell you that what you want for that carbon is resonance is better than tertiary, is better than secondary, and I'm going to draw a primary and cross it out to say no primary. What the hell does that mean? That means if I'm trying to do an Sn1 reaction and I have a leaving group here, it won't go. This won't give me a Sn1 reaction because the leaving group is on a primary. That's not happening. But if I have a double bond right here, then it will go. Why? Isn't it still on a primary? Well, when the leaving group leaves, look what's left. So one thing we have to know is if it's going by Sn1, when the leaving group leaves, where the leaving group is attached is going to be a carbocation, right? Let's say you have this and you have a leaving group. If the leaving group left, you're going to get a carbocation here. So it's going to look like that. What kind of carbocation is that? Primary. That means it's not happening. What about this? What about if I had it like that? If the leaving group leaves, then I'm going to get that. Well, that's a secondary carbocation. That'll work. Now it would be a tertiary carbocation. That'll work even better, even faster. Because notice, tertiary is better than secondary. That would give me a better rate of reaction. You know what that actually is going to... For a professor that's clever on this, they might ask you this. They might give you a molecule that has a leaving group over here, and then a leaving group over here, and show you some sort of a nucleophile, and say it goes Sn1, and ask you which leaving group is going to get replaced. Now here's a leaving group on a secondary position. Here's a leaving group on a tertiary position. Do you see that one is going to get replaced? I might even drop a leaving group on a primary position. This one will get replaced more times because it's going to have a better rate. What's the resonance thing? You're not going to see resonance unless you create the carbocation. So over here, let's say you have a leaving group. Let me just say bromine is a leaving group, right? You're not going to see resonance at all. You're just going to see bromine is on this position and this, what the hell is that? But if I break that off and draw the carbocation that's remaining, so instead of a bromine attached to that position, that carbon is a carbocation. Notice it looks like it's primary, but do you see there's resonance that's able to be done? So that is actually going to work amazingly because resonance is even better than tertiary, right? If I take away these bonds, you're not getting anything here. There will not be an Sn1 reaction because you can't make a primary carbocation. Do you remember that? Okay, so do you see that like anything you see in the rate law, will influence what the K is. For example, you see the concentration of this. So the identity of its parts will influence the K. For example, the leaving group influences the K and the type of carbon influences the K. There's one other thing we see here, which is the brackets themselves. And brackets means concentration, and concentration means the moles of this per liter of solvent. So the last thing that matters here is the solvent. And what we need, you need a polar protic solvent. You know what? I'm going to make this simple because when it comes to leaving group, there's a whole lot of leaving groups that you can have. But if you're getting thrown this at you in like really fast, then the most common leaving groups are the halogens, Cl, Br, and I. It could be, but Cl, Br, and I. It's not just water. So your professor could say water. There's tons of them. What makes a leaving group, the leaving group, when it takes electrons and falls off, it needs to be stable. Not stabilized, but stable. And what we could say from the acid-base chapter, what walks away with electrons and is stable? So you know that HI is a strong acid, because when it walks away with electrons, that must mean that I minus is stable. So I is a good leaving group. Anything that's the conjugate of a strong acid is going to be a good leaving group. See, F minus is not a good leaving group because HF is not a strong acid. So that means this has some basicity. Why is water a good leaving group? Because what is water a conjugate of? It's a conjugate of H3O+, and H3O+ is the definition of a strong acid, so water will walk off and be stable. At least that part is good. So this is going to happen in 2 steps. Sn2 is going to happen in 1 step. And it happens in this way. Like there we don't have to consider the tetrahedral structure of this. And there's a reason why I don't consider. In textbooks, they draw this as a tetrahedron. They show R going one way, you know, like with the wedge and dash. I don't care about drawing that because the second the leaving group leaves, whatever the stereochem of this was is gone because this is no longer tetrahedral, it's trigonal planar. It doesn't have a chiral center anymore. Do you see that, like, stereochem has been just destroyed until the nucleophile reattaches, and then you get new stereochem from the product. So you got a nucleophile in this case. Here I'm going to worry about stereo because of the following idea. So here you still need an sp3 carbon. It still needs a leaving group. It still has whatever groups are attached. I'm going to make it look different. These R groups don't have to be the same, so this could be R prime, that could be R double prime. But this has to happen in one single step. Well, one step or more. I know that's like rough. Like, wait, you just said it's 2 steps in 1 step. This could be more than 2 steps. It depends on who the nucleophile is and if the carbocation rearranges or not. Let's pretend this carbocation rearranging thing doesn't happen. It still could be more than 2 steps depending on the nuke. Your answer has to be a neutral thing. If the nuke is negative, when it attaches to a positive carbocation, negative and positive cancel out and they become neutral, so this will be in 2 steps. But sometimes your nucleophile is neutral. So if your nucleophile is neutral and attaches to a positive carbocation, the result is positive, and you need to neutralize by removing a hydrogen from the nuke. So there's like that neutralization step. You must notice it in textbooks. So the same thing here. This is going to happen generally in 2 steps, but if the nuke is neutral, you need an extra deprotonation step. This is happening in 1 step, but if the nuke is neutral, you need a deprotonation step. Do you see there's like this possible last deprotonation step? Okay. Here's what has to happen. And this is just what I mentioned last time about the antibonding orbital in an acid-base reaction. You've got a carbon bound to a leaving group. Do you remember when we drew this in terms of orbitals? What does that look like? You've got a carbon with an orbital here, a carbon coming out of the board orbital, going into the board orbital, and an orbital here, and there's a leaving group, and it's sharing an orbital over here. Right? That's what a bond is. On the opposite side of carbon's sp3 orbital is a little antibonding orbital. That's where the antibonding orbital is, on the opposite side of carbon's bonding orbital. And if you have a nucleophile, put electrons into the antibonding orbital, it'll cause a break of the bonding orbital, because if you think about when you combine orbitals, bonding and antibonding, if you have 2 electrons in bonding and nothing in antibonding, you have a bond. But when somebody puts in 2 electrons in antibonding, the antibonding cancel out the bonding that causes the break of a bond. This has to occur. That's why they call this a backside attack. The nucleophile attacks in the back with reference to where the leaving group is. We have to be clear on that. It doesn't attack in the back, like meaning on the left. Like if I show you over here a compound and I say over here is the BR. Do you see let's say the BR is that leaving group, right? The BR sticking out this way. The nucleophile is going to attack in the back compared to where the carbon BR bond is. So in the back means behind the board. It's going to go this way. The nucleophile is going to attack from where the dash is, coming from that side. If I show you that the leaving group BR is pointing into the board, then the nucleophile will come from where we're at, because do you see, here's the ring and the leaving group is over here. Looking at the board? Here's the ring and the leaving group's pointing here. So the back side of that is from this side. If the leaving group is over here, the back side is over there. Like it's carbon to leaving group. Wherever that bond, go to the opposite side, the other side of the carbon. So the carbon here is in front and the leaving group's in the back. You have to go more in front. This is the direction. And the nucleophile is going to attack and kick off that BR, so the nucleophile is going to end up in the front. Does that make sense? That nucleophile will end up in the front because it's coming from the opposite side. But why is it coming from the opposite? You can just memorize that it's from the opposite side. That's where the antibonding orbital is, and that nucleophile attaching there causes that bond to break. That's what. Here, what's the cause of the bond breaking? Nothing to do with the nucleophile. The nucleophile just showed up. Right? We'll talk about relationships in a second. We'll see how this is like relationships. The nucleophile comes in over here and causes the bond to break. And now the carbon is going to be attached to the nuke. But notice you have to flip around the groups. I can't draw it like this I can't draw all of those groups the same way they were pointing. That's not a tetrahedron. Do you see how it doesn't look like a tetrahedron? In order to be a tetrahedron, this R group is going to have to move a little bit to this side. This wedge will have to slide over a little bit. The dash will have to slide over a little bit. Do you see? It's called an inversion of configuration. Everything has to pop over to the other side. Does that make some sort of sense right here? Are you somewhat following this? So what you write for this rate law is rate is equal to K times the concentration of both of those things. Why both? Because there's only one step and they're both involved. So that means that you need the nuke in the rate law, and you need the carbon with the R prime and the R double prime and the leaving group. So what things, what factors that will affect K? K depends on what factors? Actually, it'll be four things. Why will it be four things? There was only three things there. Well, look. This is unimolecular, so it depended on the molecule and specifically its parts, like who the leaving group is, who the carbon is, and the solvent that's in. There's an extra part here. And that extra part is that there's a nucleophile there. So K depends on the leaving group. Just like that, you need a good leaving group over here. So like Br, Cl, iodine, water, any one of those, right? But unlike over there, K depends on the nucleophile. So you need a good nucleophile here. There you don't need a good nucleophile. What's the word nucleophile mean? It basically means base. So water is a dead, negligible base. How do I know? Because anything that has a conjugate acid that's strong is dead. See, F minus is not dead because its conjugate is weak. OH minus is not dead because its conjugate is weak. But Cl minus is dead because its conjugate is strong, right? In order to get an Sn2 really going, you need to get a nuke that has some basicity in it. So your nuke for Sn2 should have either a negative charge with no resonance, or have basicity. That was weird. Basicity. And the way we judge basicity is you are a base if you have a conjugate acid that's not strong. If your conjugate acid is strong, then you are dead as a base. So we could actually write this out like this. If you have basicity, that means your conjugate acid pKa is going to be greater than 0. How does that make sense? Because I said H3O plus is a 0, and HCl is a negative 5, and HBr is a negative 7, and HI is a negative 9. So 0 and negative 5, negative 7, and 9, 0 and smaller than that are strong acids. So bigger than 0 is a weak acid. And if it's a weak acid, then it has some base that it makes. You need a weak acid or even weaker than that. If it's a strong acid, then it makes a great leaving group. And a great leaving group is not a good nucleophile. They're opposite ideas. And this is where we get into relationships. I'm only going to give one example of a relationship, girlfriend-boyfriend. If you want, you could switch that to girlfriend-girlfriend, boyfriend-boyfriend, man and dog, whatever way you want to do this. I'm just starting with one of the ideas. Imagine the carbon is a girlfriend and the leaving group is a boyfriend. In this case, they have a relationship. And the nucleophile is actually a better boyfriend. That better boyfriend comes in and kicks out the other boyfriend. The cause of their relationship breaking up was the nucleophile made a connection with the girlfriend. Over here, their relationship was so sucky that the leaving group of the boyfriend just left already, And when it was open game, like person was alone, a nucleophile came in. The nucleophile didn't matter for what created the breakup, right? It's like a rebound relationship. Like whoever pops in there, whoever comes up with, whoever they meet, ends up becoming a connection, perhaps.
It happened right away.
That's the point. So any time after, the point is the cause of the breakup was not the nucleophile. It has nothing to do with the rate law. Here, the cause of the breakup was the nucleophile specifically. So to be a nucleophile, you can't be a leaving group. Like whoever the leaving group is somebody who's stable walking away and doesn't give a shit about reattaching and recreating a bond. But here, the nucleophile, I don't know. The better the nucleophile, the more it wants to attack, the more basic it is. The better the nucleophile, the less stable it is. This nucleophile has been to jail, hasn't seen a girl relationship in 20 years, right? It's going to really attack and push the leaving group out of the picture, kind of a thing. Like that's how that goes. You need room. If this nucleophile is going to attack backside, you need room. So first of all, so the nuke, you want some basicity. Right? Now some nukes just have a negative charge, and they're not even basic, like Cl minus. But if you have something like this, ClO3 minus, that is not going to be a nuke, because it's the conjugate base of HClO3, so it's not basic, because HClO3 is a strong acid. We started this course with ClO3 minus, I talked about this. So this is not a base, because its conjugate is a strong acid. It's a dead base, is what I'm saying. And we know that this has 3 resonance contributors, so it's not even a negative charge. See, this says you have to either have a stable negative charge, not stable, but a localized negative charge, no resonance, or some basicity. And this doesn't have either criteria. It's not a nuke. You know what the major things that are not nukes? Here's the easiest thing to remember for what is usually not an Sn2 nuke. What is usually not an Sn2 nuke is water, alcohol, or carboxylic acid. And I didn't say carboxylate. I'm not talking about this. This could maybe be an Sn2 nuke because it's got some basicity to it. It has resonance, so forget that negative charge thing. But it's got basicity to it because the carboxylic acid's a weak acid, so this is a base. I'm not talking about that. I'm talking about this. This has got no negative charge, and it's definitely not a base since it's called an acid. Right? These 3 things cannot be Sn2 nukes. Incidentally, these are the 3 things that are called polar protic solvents. So polar protic solvents can't be Sn2 nukes, if you could kind of remember that. You know what these all have in common? Neutral oxygens. A neutral oxygen is not going to be an Sn2 nuke. There's a neutral oxygen, that's a neutral oxygen. Specifically, not just a neutral oxygen, an oxygen that can do hydrogen bonding, like any kind of HOH, ROH. We're almost done with the precursors to what we're doing here. So the identity of the leaving group is important, identity of the nucleophile is important, and the type of carbon is important here also, the identity of the carbon, just like over there, but over here it goes the exact opposite way. See, here, we want resonance better than tertiary, better than secondary, because this is the order of stability of carbocation. What's difficult to do over here is break away the leaving group, and that's going to happen if the girlfriend can actually be stable on her own. Like when that relationship broke up, if she's like, you know what, fuck you, I don't need you, right? That's totally different than like, who's going to, I don't know, help me pay the rent, and I've been with this person for so long. You know what I mean? The less stable this is on their own, primary is not stable on its own. Secondary happens to have these inductive donating effects. Tertiary has even more inductive effects, and resonance stabilizes everything. So this is the order of stability. We don't need that here because we're not making a carbocation. We don't give a shit about how stable the carbocation is because there's no carbocation. You know what we need? We need room for this thing to come in and do a backside attack. And there's the most room when these 3 R groups are hydrogen. So when these 3 R groups are hydrogen, you've got absolutely nothing blocking, no steric blocking. That's why we wanted to talk about steric interactions back in Newman projections. When they're tiny little hydrogens, a nuke can come in there no problem. You know, you can't see it here. I have to show you a space-filling model. Usually the leaving group is like a bromine. Attached, chlorine, iodine, attached to a carbon, and then you have 3 groups. Size-wise for an atom, carbon would be like that. Let's say carbon is that big. Bromine is way bigger than carbon. Carbon's on this row, bromine's way larger. So if it was a bromine attached to a carbon, then it would be something like that. And then if you have 3 hydrogens in a tetrahedral arrangement, hydrogens are way smaller. So you have hydrogen, hydrogen in front, hydrogen in back. And you got all that room back there for the anti-bonding orbital, right? If I replace one of these hydrogens with a methyl group, a CH3, you have to realize that the CH3 has hydrogens on it. So instead of a little hydrogen, I'm going to have an atom as big as carbon over here, and it's going to have 3 little hydrogens on it. You see I kind of block the top approach? You can't get in there. But at least there's tons of room down here. If instead of that hydrogen over there, I get another CH3 group, now I'm really starting to block, but at least maybe a little bit in the front. If I replace the last hydrogen with another methyl group, there is absolutely no chance that you could get there. So this goes opposite of that. Here, tertiary is impossible. Resonance doesn't matter at all. It could be resonance, not resonance. You're not making a carbocation. The best here is methyl. What is methyl? Why didn't I write methyl over there? Methyl doesn't mean primary. This is methyl. If this carbon had only hydrogens on it, it's not primary. It has no connection to carbon. So that you call that methyl. Methyl is better than primary, better than secondary, no tertiary. So what is every problem that's going to be on an exam going to be for you? Secondary. And the reason it's going to be secondary is that's where there's overlap. Secondary is possible for that, and secondary is possible for this. If there's a question of is it Sn1 or Sn2, and the thing is tertiary, well, you know there's no chance of it being Sn2, it's got to be Sn1. And if it's primary, you know there's no chance of it being Sn1, it has to be Sn2. And this is going to be a little overwhelming to remember, which is why I have a backstory on this. That, like, how do you remember the pattern? It's not what you need to remember. You need to remember that this pattern goes with carbocation stability. So you want something like resonance to stabilize. This pattern goes with where there's most room, and there's most room when they're tiny hydrogens, not when they're big R groups and bulky R groups. So you're looking for hydrogens or primary, and secondary is like the limit. After that, it doesn't work. The last thing that you need over here is a polar aprotic solvent. See, solvent matters in all cases because the brackets mean concentration, right? How do you find the polar protic solvent? It's anything with an OH. Now, please don't think it's NaOH because the word protic means acidic or proton, and that's a base. That's not what I mean. I mean any kind of carbon with an OH attached. Even a carboxylic acid, that's a protic solvent. Any carbon OH, for example, ethanol, boom, you know that's a polar protic solvent. Methanol, polar protic solvent. Acetic acid, polar protic solvent, like any one of these. Ethers are not polar protic solvents because there's no H attached to the ether. I'm telling you that there's no way. I don't care what she said, it doesn't matter. An ether would be an aprotic solvent, and actually an ether is a non-polar aprotic solvent. It is both non-polar and aprotic because its dielectric constant is 4.7, and to be considered a polar solvent, you need to have a dielectric constant greater than 5. So this does not count as a... Notice the difference between an ether, like diethyl ether, and an alcohol like propanol. The OH, that can't hydrogen bond, this can. You see it's got an OH? It's some sort of carbon connected in an OH. Propanol is a protic solvent. Acetic acid is a protic solvent. Formic acid is a protic solvent. Any carbon with an OH attached is a protic solvent. Right? Glucose, let's say, if it was liquid, it could be a protic solvent because it got all the OHs, right? What's a polar aprotic solvent? This one's going to be hopefully easy. Anything that's exotic, anything that's a weird name. So if you see, I'm dead serious. That's how I teach it in the beginning, and then later we get used to it. If you see a question that looks like this, they show you some molecule with a leaving group, and then they show you some arrow, and they might even put a nucleophile in there. Let's draw some random nuke, like O minus Na plus. How do I know which one of these is a nuke? So you remember that a carbon connected to a bromine, chlorine, or iodine, that's your leaving group. It doesn't have to be in front of the arrow. It could be on the arrow. Who knows? But the point is, bromine, chlorine, or iodine on a carbon, there's a leaving group position, right? And this thing right here is secondary. Do you see that it's secondary? Because it's secondary, it could go Sn1 or it could go Sn2. So what's going to determine if this is Sn1 or Sn2 is if there's a nucleophile or if there's a solvent, right? The main thing that determines that if it's Sn1 versus Sn2, if they're secondary, is the solvent. You need that polar protic solvent, right? Here, the main thing that determines it is the nucleophile. Without a nuke to break the bond, the reaction's not happening. See, let me clarify this one more time. Here, the nuke goes into the antibonding orbital and causes the break of that bond. That's why we need a nuke. If you don't have a nuke, it's not happening. Here, what causes the break of the bond? That bond is not being broken because of the nucleophile. It's the leaving group, but why would the leaving group just leave? It's conditions that make a leaving group just leave. Like if everything is great conditions, why would the boyfriend just walk out? It's environment. So here's a question you know an answer to. If I have NaCl in a container, what does it look like? It looks like the Na and the Cl are attached, right? How do I separate Na and Cl? How would I separate Na from Cl? I think you should say put it in water. Did you realize that if I put NaCl in water, I'm going to create Na plus and Cl minus? So it's the polar protic solvent that broke up that relationship. Here it's the polar protic solvent that'll break up, count that as Na plus and that as Cl minus, and the more polar protic a solvent you have, the more it'll break up that relationship. So the cause of that bond breaking, the entire rate is really dependent on the polar protic solvent, as long as you have a leaving group and it's on a carbon that's at least secondary, tertiary, something like that. And over here, the cause is the nuke. So here, the polar aprotic solvent is not as important as over there the polar protic solvent is. So here, we almost ignore the solvent. So I could show you an Sn2 reaction over here. This is Sn2. Why is it Sn2? Because you have a leaving group on a secondary, so it could be Sn1 or Sn2. I don't see any polar protic solvent, so I can't claim that it's Sn1, but there's a base, O minus. So it's probably Sn2. And then what was I saying about the aprotic solvent? You're going to have some crazy sounding molecule down here, or letters you've never heard of, like DMF. It's like, whatever the hell that is.
No, we know what that is.
Okay, dimethylformamide, NN dimethylformamide. Who cares? Some complicated sounding crap, call it an aprotic solvent, because it's definitely different than looking at something like ethanol, which is clearly a protic solvent because it's got hydrogen bonding capabilities. Do you see the big difference? Like, here's what I would show to show that it's Sn1, right? Here's an arrow, and I write methanol. How do you know it's Sn1? Because there's no freaking nuke. How do you know there's no nuke? Because polar protic solvents cannot be an Sn2 nuke. I've written that down before. So the second you recognize that as a polar protic solvent, it can't be a nuke. So you've got a molecule with a leaving group, and you can't have an Sn2 nuke. So it could maybe be an Sn1 nuke. You see, I have to maybe reiterate it. Polar protic solvent cannot be an Sn2 nuke. But it is the Sn1 nuke. So after this, you just have to do mechanisms and figure out if it's Sn2, it's really easy. The mechanism is like really straightforward. If I have, let's say over here, a Cl, and I have this reagent, let's say NaSCH3. You see that, you have to instantly realize that Na is a metal and SCH3 is a non-metal, so in your brain you're thinking that's Na plus and SCH3 minus. That thing with a negative charge and no resonance is a base. That's a base. I don't see any polar protic solvent at all, and that is on a secondary. If that was on a tertiary, you'd say no reaction, because you can't do this with tertiary, and there's no polar protic solvent. You're going to say, I can't find the reaction, at least between Sn1 and Sn2. There might be other reactions, but just not Sn1, Sn2.
Does it get Sn2 reaction?
This is going to be Sn2 because it's secondary. There's a leaving group, so that could be either of them, and there's a nuke. And the nuke just does Sn2, which is backside attack. So what that means to you is the following. This is going to be your product. You looking? Looking at what the product is? The nuke is, the leaving group's going to leave, but the nuke comes in sneak attack from the other side. So that's why it looks like this. Do you see it came in from the opposite side? See, the boyfriend wasn't paying attention. They came in from behind. And on the other hand, if this was Sn1, the simplest Sn1 is with water. This has a mechanism to it. How do you know this is Sn1? Pretty simple. You've got a leaving group on a secondary position. That could be Sn1 or Sn2. I don't see a nuke anywhere. When I say nuke, I mean Sn2 nuke. Because there, the nuke is not what matters. I have a polar protic solvent that helps Sn1. And it turns out the polar protic solvent slows down Sn2. The polar aprotic solvent helps Sn2, but kills Sn1. See, for Sn1, the solvent really matters. And for Sn2, the solvent helps or hurts. What is necessary for Sn2 is the nuke, the real nuke. This doesn't have a nuke, because that's on an Sn2 nuke, and that's on an Sn2 nuke. Right? So that means this is only Sn1. How do you do Sn1? Here's the steps. This leaves. You show equilibrium arrows and show it leaves. So you have that and Cl minus. Next, look at the steps over there. Next, the leaving group could reattach. Well, that's why I always show it as an equilibrium arrow. Or any other base can put their electrons into this empty orbital, because there's an empty orbital here. So the solvent can put electrons into that empty orbital. And if you didn't learn about stereochem, then I would ignore stereochem here. But if you did learn about stereochem, realize what's over here. There's a carbocation. We talked about this a while ago. Carbocation has 3 bonds and a positive charge, right? One bond this way, one bond that way, and then the other bond must be a hydrogen pointing up this way, and it has to be trigonal planar, because if you have 3 bonds, you're sp2, trigonal planar. So the carbocation looks like this. The nuke, let's say water, could come in from the front and make a bond this way and turn it into a tetrahedron, or come in from the back and turn it into a tetrahedron. So you're going to end up having an oxygen connect to the front on a wedge or the back on a dash. But again, because you just started Sn2, I would ignore, just started stereochem, I would ignore that aspect and just find the constitution, deal with the constitution of this. Just like resonance, when I push arrows, nothing disappears, electrons just move. What that means right now is this oxygen will use this lone pair to connect to that carbon. So from that carbon, I draw a bond to the oxygen. That's what this is saying. This oxygen is using the lone pair to connect to that carbon. What it is also saying is that there's other things connected to that oxygen. None of them disappear. So what else is on this oxygen? 2 hydrogens and another lone pair. So I have to draw 2 hydrogens, a lone pair, and you end up realizing, I hope, that there's a positive formal charge on that oxygen. Do you end up realizing this?
Yeah.
Here's how you realize this. Every step has a conservation of charge. A neutral thing reacted with itself, broke up into negative and positive. Isn't neutral equal to negative plus positive? Now a positive reacts with a neutral, so plus and a neutral together is positive, so when they connect, it must still be positive, right? You can never finish the reaction here. You have to finish the reaction with a neutral oxygen, and the only way that oxygen is going to be neutral, I also had that in an earlier lesson, is if the oxygen has 2 bonds and 2 lone pairs. It can't have 3 bonds, because then it's like H3O+. So whenever you have a neutral nucleophile, there's always this last step that you need to remove one of the hydrogens and deprotonate it using the solvent. It'll always be the same kind of step. The solvent, which in this case is water, is going to use a lone pair to remove a hydrogen in an acid-base reaction, giving the bond, the electrons, back to the oxygen. That'll always be a last step if the nuke is neutral. You see what I mean? It's like, so it's still these two steps. It's still these two steps, but if the nuke happened to be neutral, then the result would not look like this. It would be a positive charge, and that means you'd need another molecule to take a hydrogen off that nuke and give electrons back to the nuke. You have another molecule taking the hydrogen off the nuke and giving electrons back to the nuke to keep it neutral. There's just that third step. So these are, you'll notice that Sn1 reactions, the mechanisms are way crazier than Sn2 reactions. There's like much more steps.
Is that the alkyl oxonium ion?
No, if you have an oxonium ion, actually, sorry, I was thinking of something completely else. Yeah, that's a alkyl oxonium ion. You're absolutely right. I was thinking oxyanion, and that's, you said oxonium. It's been a long day.